In this presentation, I will go over the thermocouple, do a small review of what we have done on Tuesday, and continue and end with an example of the thermocouple. So just to refresh your mind, so the thermocouple is a junction of dissimilar metals. It generates a voltage that is proportional to temperature. So this bimetallic junction, so we should have two different metals, will generate an electric potential. This electric potential or voltage created at the end of the thermocouple is equal to AT plus BT square. In some other references you see plus CT cube. Okay, but here we will just have a second order polynomial. Okay, we will see that this is generally A and B are constant, which are a function of the type of metals that we have. However, we'll see that generally these A's and B are not given. We can have the voltage in function of temperature from a table, which we will call the thermocoupled table. So these are the types of thermocouple that we have, B, E, J, K, N, R, S, T, and each one of these types, they have a combination of metals as well as range, so different range for each one of these types, and a different sensitivity, which is here an approximate number, since the thermocouple is not exactly linear, but this is just an idea of the sensitivity to compare one type to the other. If you want to do this comparison on a chart, this is what we have. Okay, so depending on the range that you have in your application, depending on the sensitivity needed, okay, so you can choose what type of and of course the budget, you can choose which type of thermocouple you need. JK are really one of the most used thermocouple in everyday application, where you see they can have an acceptable range as well as an acceptable sensitivity. So we said that the thermocouple is a self-powered sensor. It has a simple connection. It's inexpensive, very commonly available, and it covers a wide temperature range. The disadvantage is that this voltage with respect to temperature is nonlinear. The voltage output is, in terms of millivolts, a few millivolts. Reference devices needed, and we will talk about the cold junction compensation that is needed, okay, and it is least stable and sensitive compared to other temperature sensors. So talking about the cold junction, so in order to have a voltage output here measured by a gauge or a voltmeter, okay, that is really and exactly proportional to the measuring tip that I have here, the temperature of the measuring tip that I have here, I should ensure that all the other voltages coming from other junctions, for example here the junction of the voltmeter lead wire with the wire of the thermocouple, or here another one. So we have to make sure that these two or any other junction other than the measurement tip should be kept at 0 degree. Okay, since from the polynomial 0 degree will give me a 0 volt. Therefore, there will be, no effect here on the voltage measured by the gauge. So now, if one of the measurement tip, where we can call it the cold junction, in fact, if the cold junction is at 0 degree, I can enter to the table, and now from the voltage that I read, okay, I can know what's the temperature of the hot junction, which is the measurement or the measuring tip. So here, as you can see, this is a standard table. So you see here this table is in degrees centigrade. It is for a type E thermocouple and the reference junction at 0. So if the reference junction is not at 0, I cannot go in this table. We will see later I will use the law of temperatures, of voltages. The thermoelectric voltage is in millivolt. So therefore, if the temperature is 250, here is the units. So 257, for example, you go on this line on 250 and you go unit 7, so the output is 17.715 millivolts. This is how we read the thermocouple standard tables. So generally, it's not very practical to carry a bucket of ice and water to keep the cold junction at 0 degree. So practically what we do is we put the cold junction in an isothermal environment where the temperature is known. So in this way, the temperature of the cold junction here, I will call it I, will be known. Okay, how known? It will be measured by a thermistor, by an RTD, by an LM35, depending. Okay? And this is practical because this sensor here cannot measure, for example, the flame temperature. Okay? It will be deteriorated. However, it can measure this cold junction isothermal environment because it's a lab environment. It's an environment that can be an operating range between, for example, I don't know, 10 and 50 degrees, for example. So if this is known, I can use the law of intermediate temperature, which will tell me this. Okay? What's this? This will tell me that the voltage, this is E, it's the voltage. When the hot junction is at a temperature T and the cold junction is at temperature 0 is equal to the voltage when the hot junction is at T and the cold junction is at I plus the voltage when the hot junction is at I and the cold junction is at 0. شو يعني? What does this mean? Take this voltage. This is the voltage when the hot junction is at a certain temperature T and the cold junction is at a certain temperature I. So this is the voltage that I read from the voltmeter. Why? Because in real life, the here, if I have a voltmeter, the V that I'm reading here, I am reading ETI. I am reading the voltage when the hot junction is at a certain temperature T that is unknown for me, and I should know it. Okay, and the cold junction is at a certain temperature I. Therefore, when these two conditions are here, the voltage is called ETI, and this is what will be measured by the voltmeter. This one here, okay, since I is known, I can enter in the table and get. Why I can enter in the table? I can enter in the table because the cold junction is 0. This is the only condition that will let me enter into the thermocouple standard tables. So I is known, so I can go in the table and get the voltage. So I have now this voltage plus this voltage, so I have the voltage here. I will go in the table in the opposite direction in the voltage, and I will get what is the T, which is my unknown. Bear in mind, what is the objective? Here I am putting a thermocouple in order to measure what is T. So what is the temperature of the hot junction? Let's do an example. Consider a type E thermocouple, which is to be used for the measurement of a temperature with a cold junction at 20. Here the thermocouple, the thermistor, gives me a cold junction equal to 20. It has a cold junction compensation. It produces an output voltage of 12.227 millivolts. It produces an output voltage. So this is the voltage that is read by the voltmeter. What temperature is sensed by the measuring junction tip? So here I is equal to 20 degrees. T, which is unknown that I want to find, 20 is equal to 112.227 millivolts. So go into the law of intermediate temperatures. So ET0 is equal to ET20 plus E20. ET20 is known, this is the one from the voltmeter, 12.227 millivolt. EI0, E20, I will go into the table. So here 20 degrees will give me a 1.192 millivolts. So 1.192 millivolt. Therefore, ET0 is 12.227 plus 1.192 is equal to 13.419. To find the corresponding temperature, we go back into the table and we will see what temperature will give me a voltage close to 13.419. It's equal to 200. Therefore, for a cold junction temperature of 20 and for a hot junction temperature of 200, I will be reading a 12.227 on my voltmeter, millivolts. Okay? And this is the thermocouple. By this slide, I ended the overview of most interesting sensors for mechanical engineering applications. Okay? In the next chapter, we will cover the signal conditioning.